Good evening, everyone. Welcome to this Foundation Day lecture of ICTS. As perhaps some of you know, but maybe many of you who are visitors don't know, every year we mark the ICTS Foundation Day, not necessarily to the day, but within a margin of a few days. So this year we are marking it today on December 9th. And every Foundation Day we have a special lecture aimed at a broad audience, not necessarily people in the field, but somewhat more accessible audience, somewhat more accessible to a general audience by a distinguished scientist. And we've had a long list of very eminent scientists in this series. And this year we are particularly happy that we have Professor Chandrashekhar Khare, who happened to be in Bangalore at this time. So he was very sporting enough to come and spend the day. Some of you may have attended in the morning. We had a very nice conversation based on his mathematical memoir called Chasing a Conjecture, which you can actually get a copy, I think, outside, and perhaps even Shekhar might be even willing to sort of autograph it for you. So this is, if you missed this event in the morning, I think the recording will be up and you can watch it. And it, I think, really speaks to mathematicians, scientists, and so on about the lived experience of mathematical scientific creativity. So that's one amongst, of course, the book is just one of the latest achievements of Professor Chandrasekhar Khare. He is, as I said, a very distinguished mathematician who is known for his proof, together with Jean-Pierre Wintenberger, about the Serre conjecture, about which he'll tell you. But Shekhar grew up in Mumbai and did his undergraduate education at Cambridge, after which, after a year at Oxford, he moved to Caltech, where he did his PhD under the supervision of Professor Haruzo Hida, who has a very distinguished number theorist who has also been to ICTS several times. And after his PhD, he moved to the Tata Institute of Fundamental Research in Mumbai in 1995, where he was for 7 years until 2002 or so, and which is when he started seriously attacking the long-standing Serre conjecture, which after more than a decade, he finally managed to scale the peak, and in 2008 completed the proof in the most general case of this conjecture. And of course, in that time, he had moved from TIFR to the University of Utah, and after that, 2007, I think, he moved to UCLA, where he has been since. And for his path-breaking work on this conjecture, he has received a number of honors, including the Infosys Prize, the Cole Prize, the Fermat Prize, the Fellowship of the Royal Society and the American Mathematical Society, I think the Guggenheim Fellowship, a long list of awards. And but I think Shekhar also is very unique amongst mathematicians in having decided to sort of explore this process of mathematical creativity through this memoir, which has just come out 6 months ago. And I, again, encourage any of you who are interested in that lived experience of a mathematician or a creative scientist, as he says, he wanted to show that mathematics is a creative discipline like music or writing or painting, any of these disciplines. And I think his book itself brings that out. It's very rich in metaphor, in many very vivid analogies. But today he will tell us more about the background to his path-breaking work on the Serre conjecture. So I invite Shekhar to deliver this ICTS Foundation Day lecture. There will be a cultural program at 6 p.m. and then the dinner afterwards at 7:30. And you're welcome to all of them. Please keep your phones on silent mode. Thank you.
So thanks, Rajesh, very much for the kind words. It was a lovely conversation we had in the morning, and I really enjoyed it. Thanks for being so enthusiastic about my book. As a first-time author, one is very sort of gratified. People kind of say good things about the book, and I'm very happy that the book engaged you. So I would like to wish ICTS a happy 18th or 10th or 6th birthday. There could be various interpretations of how old ICTS is. It's the first time I'm coming here. It was a long drive here. We kind of got delayed, but it was worth it. It's a lovely campus, and it's very nice to be here. So this lecture in some ways is supposed to be a mathematical complement to the book I wrote. The book has some kind of mathematics in it at a very, very impressionistic level, because when I wanted to write this book, I just wanted to talk about the process of mathematical discovery rather than what was being discovered. But then my editor and various people told me that doesn't work. You can't just say that you're drinking wine and walking and thinking. You have to say what you're thinking about. I did put in I did try to sort of, in the book, sow mathematics at regular intervals in the book, and kind of making a point of intertwining the biography of the mathematician with the biography of the mathematical ideas in some ways. So the book is a mathematical memoir in terms of being a memoir of a mathematician. It's a memoir of the mathematics the person is doing, and also a memoir of the interaction between the two, the process. But this lecture is going to be a kind of a little bit of a deeper dive into the mathematics and try to kind of spell out a little bit what is left vague. It is still going to be at a rather impressionistic level. I'm still hoping to not lose too many of you as we progress through the lecture. So it's going to be at a somewhat qualitative level, but a little at a more granular level than the book itself. So let me jump right in. So actually, another thing I should say is that when I try to convince readers, people, my friends, for example, that they should read the book, not be put off by the mathematics, I tell them, don't pay too much attention to the math, engage with it to whatever extent you can. It's not essential to understand the mathematics. So for example, I mean, in my department at UCLA, my colleagues have read the book. They're, of course, professional mathematicians. But if someone in a different area might not be able to really get all the nitty-gritties of what I'm doing if you just look at the book. So it's supposed to be kind of just very impressionistic, but okay, I'm going to try and flesh out the ideas a little bit here. So in some ways, I'm going to, the two main mathematical characters, so in this lecture, I'm going to emphasize the math of the book. We've already discussed the process and sort of the human element of the story, but I'm going to now sort of focus on the math. So the two main protagonists of this story, the mathematical story, are Galois and Ramanujan. Right? So these are two of the most romantic figures in mathematics, in world mathematics, because unfortunately they had very tragically short lives. Galois, I think, died at the age of 20 or 21. Ramanujan at 32. They also kind of difficult lives. And I think unlike most mathematicians, scientists, unlike artists, right, are recognized in their lifetime for the work they do. Some of my ideas kind of have a certain compelling logic to them in math. And the ideas are accepted. You don't die unsung and like Van Gogh or someone who will kind of struggle in his life and then be recognized posthumously. But Galois is sadly a case where somehow he did not get the recognition he should have in his life. But there is a certain romantic charge to their lives because they died so young and they accomplished so much in spite of all the odds against them. So the two characters, or the two sort of mathematical protagonists are called Galois symmetries and Ramanujan symmetries in honor of these two mathematicians whose kind of work led to these concepts. I mean, the Galois symmetries is kind of a variation of a name in the literature. It goes by a more technical name, Galois representations, but I thought symmetries is a kind of kinder word. it'll put off less readers. And Ramanujan symmetries is kind of some other kind of symmetry. These are called something totally different in the literature, in mathematical literature, so it's a kind of made-up name. But somehow, as I was using Galois symmetry, it seemed a good way to balance it out by using another name. And also because Ramanujan's work is certainly very sort of related to the kind of thing I'm talking about and what are called modular forms in the literature. So the two symmetries are the protagonists are called Galois symmetries and Ramanujan symmetries, and somehow the book is about the story of these two symmetries, how they kind of interacted with each other and how they've influenced or been a very central part of mathematics since the 19th century. Galois lived, I think, in the early 19th century, Ramanujan in the early 20th century, and the work they've done still continues to be highly relevant and somehow transformative. Okay, so this is these are the two characters, and these are the pictures of them, Galois and Ramanujan, which were also there in the nice poster ICTS has made. All right, so this the mathematical plot of the book is like a quest narrative. I was trying in my book as a kind of with a foolhardy optimism to try to aim it at the general reader. I don't know how far I will have succeeded at the end. But now, as I said, this is a more mathematical introduction to these symmetries and the role they've played in number theory. So the mathematical quest of this book is kind of a quest driven by trying to prove Serre's conjecture. So I'll try to say what Serre's conjecture. Jean-Pierre Serre is one of the great figures of 20th century mathematics. He's still alive. He's going to turn 100 next year. I kind of saw him, I think, 2-3 years ago, and he's still a vigorous mind and kind of still thinks about mathematics every day. So I proved this conjecture in joint work with my French colleague, Jean-Pierre Wintenberger, in 2009. So there's distinctly a French and Indian theme to this mathematics, to the book and to the math. So I started working on this conjecture when I joined TIFR as a young sort of graduate, as a young postdoc, relatively young postdoc, not as young as Galois, in 1995. And somehow I started focusing. Serre's conjecture became my kind of moonshot or holy grail to keep in sort of sync with this theme of quest. It became I wanted to think about it. I certainly I was not certain how far I would get, but I wanted to kind of let the conjecture take me on a journey. So the Serre's conjecture roughly states that these two very, very different symmetries, right? These symmetries are actually radically different, but the Serre's conjecture says that they essentially have the same DNA, that they're actually just different names or they are kind of very related to each other. So my plan for this talk is first of all to introduce you to these symmetries and then talk about Serre's conjecture, which kind of tries to put them together as two aspects of one common kind of thing. Okay, so to keeping with my kind of, I'm going to introduce you to as like have kind of dramatis personae and then Act 1. So Act 1 is, so the entire subject kind of got started in a way. One can draw a line between Srinath Ramanujan's work in a paper he wrote in the 1916, and then somehow that led to a continuous development of ideas, kind of cutting across the entire 20th century, because people kind of, there were remarkable observations he made about a certain set of numbers, which are called tau n. And the kind of, it intrigued many mathematicians to find out what is the explanation for these phenomena he has discovered. Ramanujan, to some extent, was a phenomenologist, right? Discovered phenomena. And kind of the task of mathematicians then was to flesh out or prove these things. Okay, so the paper of Ramanujan in 1916 is called On Some Arithmetical Functions, published in spite of the modest title, the observations in this paper had a huge influence on the development of number theory. And so though one more thing I should say is that I'm talking about a conjecture which was proved like maybe 20 years ago, 15 years ago, but it still continues to be somehow quite a central theme in number theory, because Serre's conjecture has been proven, but it is kind of it is just a paradigm of a general phenomena. So so Serre made a conjecture in a particular case, or he made a conjecture, but one can generalize the conjecture, and as people have done. But in fact, no other case of Serre's conjecture is known beyond the one, or generalized versions of Serre's conjecture is known beyond the one we proved 15, 20 years ago. So somehow it's still at the forefront of research, these kind of the kind of things Serre set up in motion. So it's part of what is called in general the Langlands philosophy, and most things are unknown about this. So it still continues to be kind of driving mathematical research in a certain area of number theory. Okay, so Ramanujan made these observations, I'll come to them, and the conjecture Serre made in the 1970s and 80s Sorry, the conjecture was made in essentially 1970s, and then he refined the conjecture in the 80s. Is in the line of these developments, which started with Ramanujan's paper in 1916. And I want to trace the evolution of ideas from 1916 to 1970 or 1980, and to the resolution of the conjecture in roughly the first decade of the 21st century. Okay, so Ramanujan's paper, of course, when you look at, I mean, in some ways, I'm someone who doesn't know a lot about Ramanujan's mathematics. In some ways, this is the only paper I know very well of Ramanujan. But if you look at the paper, if you look at it from the modern eyes, right, it seems very strange. It is just like a flood of formulas. It's it's not written in a way which kind of invites you in terms of it doesn't gently introduce you to the themes and then. So it's kind of written in the style where there are lots of formulas, right? Because he was a formalist, he was a genius in terms of finding patterns and formulas. So he just starts off with this infinite product. So what you take from this is that he kind of defines a series of numbers which are called tau n. In honor of Ramanujan, this is called his tau function. And his focus was in some ways on trying to understand these numbers tau n, which I've written down. They are the coefficients of this infinite product when you expand it as a power series in X. So Ramanujan studied these. I'll kind of try to make these numbers more sort of relatable in a bit. So Ramanujan studied these values of tau n in his 1916 paper. Right? His interest was in estimating some convolved sums of some quantity, and these showed up as error terms in what he was trying to estimate. Right? So some of the problem he was interested in at that time has fallen by the wayside in some ways. But the error terms which showed up in his work, those have been a central they've been a focus of tremendous mathematical interest and work since he kind of identified certain properties of them. Okay, so in the work of Ramanujan, in that 1916 paper, you find this very table for the first 30 values of tau n. Right, so there's tau 1, tau 2, and they are all over the place, right? There's a sequence of numbers. But Ramanujan had could look into the tea leaves of these numbers and kind of just find patterns and divide, so he had this uncanny intuition, which kind of led him to first of all latch on to these numbers as something significant, and secondly to find interest in them, find interesting mathematical sort of patterns. So in his 1916 paper, the above table, the table I just showed, appears as a certain table. So for one thing, he was interested in because they were error terms. He wanted to estimate how large they were. So for one thing, if you look at the paper, one can think that tau n grows rather quickly. The growth is not exponential in n, but it's somehow Ramanujan could prove that it grows roughly like n to the 7th. Right? So somehow it grows like a polynomial of degree 7 in terms of n. So Ramanujan, with his remarkable intuition, stared at these 30 values. I'm sure he must have computed some more on the side, and made some very bold and beautiful conjectures, which proved to be tremendously influential because people kept coming back to them over the following decades. And even now, I mean, the conjectures, there's something called the Ramanujan conjecture. The first form of it he made has been resolved, but the general Ramanujan conjecture is one of the central themes of the theory of automorphic forms and a certain kind of number theory. Okay, so anyway, we're going to stay with these numbers tau n, and maybe I should say that you can, I don't know in this auditorium whether it makes sense, but if you have any questions, please feel free to interrupt me and I can address them as best as I can. Okay, on the basis of these 30 values, Ramanujan made remarkable and what turned out to be highly influential conjectures. And one can indeed treat these numbers and the properties Ramanujan observed of them as a starting point on the road to Serre's conjecture. So now Ramanujan, in fact, it's not clear how Ramanujan thought of these numbers tau n, right? Somehow there's a certain mystery to everything Ramanujan has done. One doesn't know how he thought about them. So for example, this function which I wrote down, which is just like I wrote down an infinite product and expanded it as a power series, maybe he thought of it just as in some way, some combinatorial type of object. In fact, I've asked Serre, did Ramanujan think of it in some more structural way as a modular form or something? And Serre said that Ramanujan did not need to think of it like that because even without knowing what a modular form is, or he may or may not have known exactly, but he had the intuition of what kind of object it was. And he somehow knew that it had something to do with GL2 or something like that, yeah. So it is, but from the modern point of view, or from a later point, it's useful to think of this function, right? This function which I started, this kind of rather arbitrary looking function. You're looking at a product and you're raising something to the 24th power, etc. It looks pretty random. But actually it turns out to be a function with certain properties, which are kind of ubiquitous in mathematics. These are the so-called modular forms, the cusp forms. Okay, so I'm going to, you start thinking, give this function more structure, when you interpret this variable x as some sort of power of e raised to the power of type 2 pi I z, which is called generally in the literature q. Okay, so Ramanujan symmetries. So now I'm introducing to you the Ramanujan symmetries, right? So these are, at a more technical level, these are certain functions on the Poincare upper half plane, or there are certain functions with lots of symmetries, right? And these symmetries have their origin in some of matrices of 2 by 2 matrices. Okay, so so we consider the space. I'm going to kind of plunge into definitions so much. Again, if you don't want to think about this too much, you can just think of this as these are kind of some functions coming from analysis, complex analysis. And they are holomorphic functions, complex analytic functions on some Poincare upper half plane. I tried to use ChatGPT to draw this picture. So this is the Poincare upper half plane. And so the Poincare upper half plane kind of, so the reason why where the word symmetries enters into the lectures is because the holomorphic, the upper half plane has lots of symmetries. So one symmetry is a translation symmetry. You just send a number, a complex number to its translate by 1, z goes to z plus 1. And then there's another more subtle symmetry, the Mobius inversion, which sends z to minus 1 upon z. Right? So the modular forms are just functions on this upper half plane, which is just kind of the upper half of the complex plane, which kind of have good properties under these kind of symmetries which act upon the upper half plane. So anyway, all you have to think about is modular forms, which in the book are called Ramanujan symmetries, are some sort of analytic functions with many symmetries. Now, by the dint of them having this sort of symmetry under z goes to z plus 1, they kind of get a Fourier expansion. You can expand them in a power series in the variable q, which is e raised to the power of 2 pi I z. And they satisfy this transformation law under Mobius inversion. So f of minus 1 upon z, which is some sort of reflection in the circle, is equal to z to the k, and that k is called the weight of the modular form. Right? So these are sort of modular functions with certain symmetries. In some ways, they're higher analogs of trigonometric functions. Right? Trigonometric functions are functions in the real line with a symmetry under z goes to z plus 1. So these are symmetries, these are functions with sort of more complex symmetries. But somehow one of the, yeah. So this is a modular form, okay, for those who want to look at the technical definition, they're functions on the upper half plane, so that under Mobius transformations by the action of the group SL2Z, 2 by 2 matrices over Z, they transform in this way. And so these are modular forms, and within them, there's a subspace which kind of has a particular behavior as you wander off to infinity. So these are the so-called cusp forms. The constant term of their Q expansion is 0. Okay, so this is like a little bit technical mumbo jumbo. Okay, so and now the question of whenever you define something, the first question is whether something exists, right? Whether this is a non-zero space, and in fact, one can rather explicitly write down some modular forms. These are the so-called Eisenstein series of weight k, and they have this explicit Fourier expansion. Their constant term is some very mysterious term in some ways. It is kind of related to the values of the Riemann zeta function. One of the great outstanding problems in mathematics is the Riemann hypothesis about this Riemann zeta function. But their non-constant terms are kind of rather simple arithmetical functions. The sigma k minus 1n. They are just sums of the k minus first powers of the divisors of n. Right, so somehow all you can take from this is that, okay, you can explicitly write down for k even and sufficiently large weight, bigger than or equal to 4, you can write down explicitly in modular form, right, whose Fourier coefficients kind of are rather explicit. All the terms except the constant term are rather explicit. The constant term also in some ways is given by the formula, but it has mysteries lurking in it. All right. So anyway, so modular forms have this behavior that the thing I wrote down is form. Look at the line spanned by it, and then there's a complementary subspace which is given by the space of cusp forms, which are function modular forms with the property that they vanish at infinity. All right, for those who've never seen this before, and you can just think of these as analytic functions of which come from some of the land of calculus in some ways, but with symmetries, right? So that's Ramanujan symmetries. And it turns out that the function Ramanujan was looking at is a Ramanujan symmetry, or the modular form of weight 12 and level 1. It's a cusp form of weight 12 and level 1. Okay, so I'm not going to, given the nature of the lecture, I'm not going to sort of obsess too much about all the technicalities. You can write down you can write down dimension formulas, for example, for the space of these space of cusp forms or modular forms. And it turns out, now the one thing I would like you to perhaps retain from this is the Ramanujan delta function, or the function Ramanujan was looking at, this fx, when you put in x equal to q, that is the first instance of a cusp form in the realm of level 1 forms. So the first time you have a cusp form is in weight 12. Anything in weight less than 12, there is no cusp form in level 1. So in life, in general, if there's the first time something happens, it's very interesting, right? So somehow the delta function is very interesting, and it has been sort of very intensively studied since some ways the 19th century, because this function in some ways predated Ramanujan, but it's called Ramanujan because of the fantastic kind of observations he made about it. Maybe Jacobi and people like that in the 19th century also had studied the delta function. All right, any questions? Okay, so now I'm hoping to now get to a more qualitative level of discussing these ideas. So the tau n's are some sort of Fourier coefficients of the cusp form of weight 12 and level 1. Right, so if you want to, if you look at Ramanujan's paper, I'm kind of saving you many of the formulas which you would be overwhelmed by when you look at Ramanujan's paper. But this is one formula, right? So delta is equal to this product expansion. And when you expand it out, one writes the coefficients of the power q to the n as tau n, right? And this tau n is called the Ramanujan tau function. And this delta function, which is now a cusp form of weight 12 and level 1 in our language, a Ramanujan symmetry of weight 12 and level 1, is called the Ramanujan delta function in honor of Ramanujan, because he made it his own by all the sort of remarkable sort of things he asserted and sometimes proved about these Fourier coefficients, tau n's. Right? So somehow that is what Ramanujan symmetries are, and somehow in the book also I kind of focus on this delta function. The delta function played a role in Serre formulating the conjecture, and in some ways one of the first cases we proved of the conjecture was also related to the delta function. So somehow it's a nice story that whatever Ramanujan did kind of continues to feature prominently in this work. Okay, so here's what Ramanujan conjectured, purely by just looking at these first 30 values of tau n, or maybe more, and just kind of observing, right? He observed that this function is multiplicative. That means tau of the product of two numbers which have no common factors is the product of the respective tau. So tau mn is equal to tau m times tau n, when m and n are co-prime. But on the other hand, when you're not, for tau at prime powers has this kind of slightly recurs at this kind of behavior, where you can express it in terms of the smaller values of value of tau at the smaller powers of p, but it's not quite totally multiplicative. There's some kind of formula which expresses them. So these were the first two conjectures, which was about the properties of these functions tau n, some of them multiplicative properties. And the last conjecture, so Ramanujan knew that somehow he knew that the size of tau p was roughly like p to the 6 or something like that. But then he asserted that actually it should be tau p, the absolute value, should be less than or equal to 2 times p to the 11 by 2, which is, if you do the arithmetic, it's 5.5. So he was asserting that that's less than or equal to 2 to the p point, 2 times p to the 5.5, and he already knew it was p to the 6th, right? So it's very, very small looking power saving. So in some ways, somehow this is remarkable because in the 19th century, ever since the remarkable work of Dirichlet on his theorem about prime numbers, people had considered certain kinds of L functions. So now instead of looking at tau n qn, you can somehow make a Dirichlet series out of it by looking at the L function associated with delta and writing it as tau n upon n to the s. Right? So somehow some kind of transform of this original sort of Fourier expansion of delta. And basically, people had looked at some function like this, L something S. That something was kind of what is called Dirichlet characters. And then in today's language, we would call them degree 1 L functions. So what Ramanujan was asserting was that this kind of thing you can write down formally should have a Euler product expansion that should sort of factor into certain expressions indexed by primes. Right. Anyway, so the remarkable thing about Ramanujan is that this is the first time in history that someone wrote down a degree, an L function of degree greater than 1. Right. And in his formula, in his paper, you do find this expression of the first two conjectures of his. That these two conjectures are equivalent to asserting that this L function, written down in this way, factorizes inside over the prime numbers. Right. So somehow that was. So what happened was that he made this conjecture in 1916, and very quickly, the first two conjectures were proved within a year. right? So model, I think an English mathematician perhaps working in Cambridge at that time, or somewhere in England anyway, proved these conjectures within a year or two. And what he did is that rather than looking at these just numbers Darwin, right? Because in the mathematics, in some ways, one progresses by endowing something with structure. So these Darwins are just numbers, right? And perhaps I mean, even Ramanujan couldn't prove his conjecture. So somehow it was not that easy to prove these first two conjectures. But what Mordell observed is that if you introduce another kind of symmetry in this situation, the so-called operators Tn, which he introduced in this particular case, and then were vastly generalized by the German mathematician Hecke. So there are certain operators which act upon these spaces, and their action can be diagonalized. And these operators, right, they have a structural meaning. They are not just mere numbers. They are sort of operators which have a definite sort of significance. There's some averaging, there are some averaging kind of operation. And because they have this meaning, you can prove what Ramanujan had asserted for tau n for these operators. Right? So somehow this is this kind of, I'll allude to this idea of categorification. If you want to prove something, you endow it with more structure, right? So nowadays, it's fashionable to use the word categorification, which I'll use. So what he observed is that these operators he defined had the properties which Ramanujan was looking for at the level of these operators, right? But now, what is the connection with tau n? It turns out that the tau n, sorry, delta n, tau n, it turns out that the tau n's are the eigenvalues for the action of these Hecke operators. Right? And somehow if you know something at the level of operators, then you can deduce it logically for the eigenvalues. Right? So there was this idea of then promoting these numbers, tau n's, which are merely numbers to begin with, but giving them some meaning as eigenvalues of certain operators called Hecke operators. Right? Again, I'm not going to sort of, this is not really a formal math lecture. I'm going to skip over a little bit of this. What turns out is that the delta function, which has this expression as summation tau n q to the n, the tau n's turn out to be the eigenvalues for the nth Hecke operator, right? And because tau n's satisfy the multiplicative properties Ramanujan conjecture, as a corollary, you deduce that tau n also satisfy those properties. So very quickly, basically the story is that there was this Ramanujan symmetry delta. He asserted these two properties of tau n, and very quickly it was proved. But as a consequence of some idea, it was not some mindless proof. You had really to come up with a new idea to prove Ramanujan's conjectures, those two conjectures. Okay, so now this I've anticipated this slide. This is an idea of categorification. You try to prove something about numbers by, in this case, you first of all recognize this rather strange looking function which he wrote down, f of x, as a modular form of weight 12 and level 1. In fact, as a cusp form of weight 12 and level 1. Then you realize tau n, these Fourier coefficients, as eigenvalues of operators. And these eigenvalues satisfy the properties Ramanujan is asserting for these so these operators satisfy the properties Ramanujan is asserting for the eigenvalues. And then you deduce, as a consequence, what Ramanujan conjectured for tau n. Right, okay, so this is the story of tau n of the first two conjectures. So now I should say that these modular forms, or what are called Ramanujan symmetries, are ubiquitous in mathematics. There's a well-known quote of the German mathematician Martin Eichler that there are five fundamental operations in mathematics: addition, subtraction, multiplication, division, and modular forms. Right? Somehow because he's just trying to portray that modular forms are just everywhere, and somehow they're very powerful, ubiquitous, and universal in some ways. I mean, in some ways, if you look at Lewis Carroll, which as I joke in the book, now I forget the exact quote, but he talks about these four operations as uglification, and so I don't know the word, so this is a different kind of classification of these operations. Okay. All right. Now, actually, the last conjecture, where Ramanujan conjectured that the value of tau n was less than or equal to 2 times p to the 5.5. That kind of survived. I mean, no one could prove it for the next 6 decades. Right. So the third property conjecture by Ramanujan turned out to be a really tough one. No one could prove it for 60 years. Then in 1975, then in the early 70s, Deligne proved it as a consequence of a proof of his way of another set of conjectures of this French mathematician André Wiles, who I alluded to in the morning sort of discussion. So it was proved after a great mighty struggle and as a consequence of developing a lot of theoretical mathematics. So all one was doing, right, at the end of the day was going from p to the 6 to p to the 5.5. But somehow that 0.5 took 60 years to prove. So the power saying of 0.5 conjectured by Ramanujan took a very long time to prove. And as I said, this conjecture is just a paradigm. I mean, just a sort of conjecture. If you generalize that conjecture, as people have done, it turns out to be one of the central conjectures in one of in the theory of automorphic forms, which is the generalization of modular forms. And it certainly drives a lot of work even now. So the conjecture sort of has been very influential even after, and continues to be influential even after it has been proved. All right, so G.H. Hardy, the person who played an important role in Ramanujan's life, and generally was a fan of his mathematics. As he says somewhere, his interaction with Ramanujan was one of the most romantic episodes of his life in terms of it really transformed his mathematical career and whatever. But Hardy was, like, in spite of his great regard for Ramanujan, he was slightly skeptical about the importance of the sharpening that Ramanujan had conjectured, and wrote, "We seem to have drifted into one of the backwaters of mathematics." He said this about this conjecture. But Hardy did qualify this by saying that maybe he doesn't see the point of it, but maybe there is a point because someone of the stature of Ramanujan is saying that it is interesting. So he qualified his skepticism by saying that the problem might have some features which made it not unworthy. This is a very British double negative or something, which made it not unworthy of Ramanujan's attention. Okay, so this is so in some ways Ramanujan's intuition, right, was kind of triumphed in the end over Hardy's skepticism, because these conjectures have turned out to be highly, highly important, influential, central. Okay, so now the other thing Ramanujan observed, which is actually even more relevant for the Serre conjecture, he observed also like a remarkable congruence. Right, a congruence of numbers is somehow two numbers which are different but which leave the same remainder when divided by some number like 691. Right, the 691, it turns out to be a prime. It's called, maybe one calls it a Ramanujan prime. If you look at Serre's address, email address, it's jp-serre691. Okay, so somehow this number 691 is kind of dear to many people because of the properties Ramanujan observed about it and the role they've played in mathematics ever since. So he observed a congruence. So what is a congruence? But people are kind of sort of maybe a little bit far away from number theory and all that. And congruence is just two things coming together. So in some ways, it's like a metaphor, right? It's you're linking two things, two different things, but which become the same mod p, mod a number, mod 691. So you made this remarkable, and first of all, it was rather strange to look for congruences of the Fourier coefficients of a complex analytic function. It's almost like mixing categories. Right? No one in their right mind in some ways would do it, but Ramanujan had the sort of kind of, his imagination broke no boundaries. So he kind of looked at this thing and kind of observed this congruence. So tau n, yeah. Yeah, sigma 11n is the sum of divisors of n to the 11th power. Yeah, if I had a blackboard, I could have kind of complemented this by, yeah. So anyway, but the point about this is tau n is a rather mysterious function. There are no explicit formulas for it. But sigma 11n is a very, you can write down the function, right? So somehow these two, tau n, which is a totally kind of, it has no closed formula. But when you reduce it mod 691, when you look at its remainder when you divide by 691, turns out to be a very elementary function. Right, so there was a certain kind of, it simplifies mod 691. And again, it's rather strange to look at congruences, which is a very kind of arithmetic operation for coefficients of complex analytic functions in some ways. But Ramanujan did it, and again, it may have seemed a mere curiosity in some ways, right? What is the point of this? But Ramanujan kind of asserted this, and again, over the decades, this turned out to be like a very fruitful thing to think about. So in some ways, the takeaway from this is that there's something called Ramanujan symmetries, which Ramanujan studied a particular case of. He made some strange-looking observations about them, but because of the fact that he was a remarkable mathematician with tremendous intuition, it turned out that what he did was very important. And all this started in 1916. Yeah. Yeah, I mean that some of the primes, the exceptions, the primes associated with this delta function are the primes 2, 3, 5, 7, 23 and 691. So 691 is not the only prime which is significant for tau for this function, but there are a few more primes, but they're just finitely many. So these are the primes, speaking to addressing, these are the primes for which tau n, when you reduce tau n modulo those primes, so when you look at the remainder, tau n leaves and divided by those primes, has a particularly simple expression. So these are, I mean, Serre and Swinnerton and Dyer, when they studied these things, they call them the exceptional primes for this function. So there are 5 or 6 of them, and 691 is the largest prime. So the 691 somehow has this feature of, it's like a Goldilocks prime, neither too small nor too large. So somehow it stays in the mind. 2, 3, 5, 7 are too small. But 691 is a nice looking prime. So it kind of, it has stayed fresh in mathematics. And okay, so no, as I said, no one before Ramanujan. And 691 has a significance that somehow 691 divides the numerator of the 12th Bernoulli number. So for those who want to dive into the mathematics, it does show up in a natural way in this context. So no one before Ramanujan had delved into the possibility of Fourier coefficients of complex analytic functions having interesting arithmetic properties. As I said, this is almost mixing categories. So as I said, I mean, there were other similar congruences for a finite list of primes, 2, 3, 5, 7, 23, 6, 91. I don't know how many of these Ramanujan observed, because many English mathematicians, Indian mathematicians working in the decades after Ramanujan observed more congruences. So the feature of these congruences, mod P, is tau n, right? Tau n is this, you don't really need to know you don't need to remember the formula for it, but it's kind of a series of functions, a series of numbers. One of the properties of it is that there's no closed formula for them, but when modulo these primes, they simplify. Right, and then people are mystified. Or there was a natural question, what is the significance of these set of primes? 2, 3, 5, 7, 23, 6, 91. Right, sometimes people have these games where you're presented with a set of numbers, you have to figure out what is significant about them, or what is the next number. So in this case, so there was a mystery why people wanted to understand why do these primes show up? And this is the task Serre, Jean-Pierre Serre, the mathematician I talked about, and the British mathematician Peter Swinnerton and Dyer set themselves. They wanted to understand what is the significance of these primes. First of all, they wanted to prove that these are the only primes for which tau n simplifies when you reduce it modulo p, which is to say when you look at the remainder of that function tau n with respect to that prime p. So the explanation for these congruences given by Swinnerton, Dyer, and Serre, working kind of together, and the Ramanujan bound proved by Deligne in the 1970s, both lay, right? So now I'm going to segue to the Galois symmetries. Both lay in the Galois symmetries attached to delta. Right, so some of these were so this is we are talking about the world of complex analytic functions, and we are talking about arithmetic properties of Fourier coefficients. But now we are going to switch to a completely different world, which is the world of algebra in some way. So we're going to go from analysis, complex analysis perhaps, to algebra. So this is the world of Galois symmetries. So this is Act 2, in which I'm going to tell you about Galois symmetries and introduce Galois symmetries and the role they play in Serre's conjecture and in Serre's explanation of Ramanujan's observations. Any other questions? Yeah, perhaps I've gone too fast, but all I want to take away from this is the Ramanujan symmetries. They're mainly analytic kind of in nature in some ways, and Ramanujan observed some things about these numbers tau n, but the explanation for these observations is going to come from a totally different world, the world of Galois symmetries. Okay, so what are Galois symmetries? I mean, most of us, probably hopefully all of us remember quadratic equations from high school or polynomial equations of degree 1, 2, 3, etc. So example, in this book, right, in this book I'm assuming, for this memoir I've written, I want to assume that I say that there are no prerequisites for the mathematical prerequisites for the book. And there is this famous joke of Stephen Hawking where he said that every equation you write down halves the number of people who will read the book, though he did very well though maybe his book has no equation, but it has one equation, all right. So maybe even my book has one equation. So I hope my book will sell as much as his. And his equation is very complicated, E equal to mc squared perhaps, right? But this is my equation is very simple, x squared minus 5 equal to 0, right? So somehow I'm going to illustrate Galois symmetries by thinking about this very simple looking polynomial, and it is simple. It is an elementary polynomial of degree 2, x squared minus 5, right? We know what the roots are, square root of 5, negative square root of 5. Now in this case, I'm going to not define what is a Galois symmetry. Again, for those who know about what I'm talking about, this is actually called Galois groups or Galois representations, but I'm going to use this kind of more colloquial, friendly word, Galois symmetries. And I'm going to focus on this case, x squared minus 5. In this case, the Galois symmetries are basically legal permutations of roots of polynomials. These are permutations, ways of rearranging the roots, solutions of polynomial equations, which preserves all preserves all the relations between the roots. In any case, for this particular equation, the Galois symmetries are very simple. They're just two symmetries. One is the lazy symmetry, which does nothing, right? Which sends each thing to itself. It sends root 5 to root 5, minus root 5 to minus root 5, the identity. And the other one is something which switches them, right? The permutation. So you can think of these Galois symmetries as 1 and minus 1, which act on the roots of this equation, x squared minus 5 equal to 0, by multiplication by 1 and minus 1, right? So in the book, I make this analogy, I make this kind of image that you can think of the Taj Mahal, and it has this famous bilateral symmetry. If you imagine a mirror or plane going down through the middle and reflecting across the mirror, it will preserve somehow the shape. So yeah, so somehow symmetries, the pitch I make for symmetries in the book is numbers quantify our idea of size, symmetries quantify our idea of beauty and balance. Right? So somehow that's my slogan for numbers and symmetries. And some of the magic or whatever, the mathematics I do or in my area is that we use symmetries to study numbers, right? So some of that's in general the theme of the kind of math, the reciprocity laws or whatever some of us do. Okay, so now these symmetries, they are going to actually, for each prime q, right? So somehow for each prime q, there's going to be a symmetry coming from this equation x squared minus 5 equal to 0, which in some ways is related to how many solutions does this equation have when you look at it mod q. So x squared minus 5 equal to 0 has no solution in the rational numbers, but somehow it has some rather erratic behavior or seemingly erratic behavior when you look at how many solutions this equation has mod prime. So in the sense when you look at, suppose I'll give you an example, okay? So if you look at the equation, if you look at the prime 13, you can ask how many solutions does x squared minus 5 equal to 0 have in the world of numbers mod 13, which is to say when you look at, sorry? Yeah. They act upon the roots of a polynomial equation. Yeah. Every equation gives rise to its group of symmetries, and they act on the roots of this equation in the world of complex numbers. Yeah. So in some ways, Galois' philosophy was not to directly try to attack finding formulas for roots of equations, because that turned out to be kind of an impossible, very difficult thing. Instead, he tried to understand roots by studying something more abstract, which is the symmetry properties, right? So somehow this was his great discovery. So I'm going to look at this equation, very simple equation, right? But what I want to illustrate is in this very simple equation, there lurk mysteries, and lots of interesting mathematics arises, right? So by just looking at this equation slightly differently. So instead of looking at the solutions of x squared minus 5 equal to 0 in the world we know, root 5 minus root 5, in the complex numbers or in the real numbers, you can ask how many solutions does it have modulo a prime, right? What does this mean? I'm going to look at x squared minus 5 equal to 0 and see, plug in values, let's say look at the prime number 13, and plug in the values of x from 0 to 12, and see whether if you evaluate these numbers at the square of those numbers minus 5, does it ever become 0, right? So you're asking whether 5 has a square root mod 13, whether there's a number whose square gives the remainder of 5 when divided by 13. So for q equal to 13, the equation x squared minus 5 equal to 0 has no roots mod 13. Right, you can do that. You have to just plug in the numbers x equal to 0, 1, 2, 3 up to 12 and see if you ever get a remainder of 0 when you divide by 13. So this equation has no solutions mod 13. On the other hand, when you look at 19, it turns out it has two solutions. And as you can check, maybe you can do the arithmetic for both these particular cases. For q equal to 19, if you look at x squared minus 5, the 5 does have a square root mod 19. If you plug in x equal to 9, 9 squared is 81, right? And it leaves a remainder of 5 when you divide by 19. So 5 does have a square root. It has two square roots mod 19, plus 9 and minus 9. Right, so the number of solutions of this equation mod 19 is 2, mod 13 is 0. Okay, so now, so this is like point counting. You're counting the number of points of polynomial equations when you reduce that equation modulo various primes. So looking at this polynomial equation, you can associate some certain local symmetries at primes, which are basically, we're just going to count the number of points of this equation, which typically is either 0 or 2, and just I'm going to subtract 1 from them, right? For a little bit arbitrary, but okay. So the local Galois symmetry at Q is the same as, is by definition, NQ minus 1, where NQ is the number of solutions of the equation x squared minus 5 equal to 0 mod Q. And then you just subtract 1. And so this number, as you vary the prime Q, is either 1 or minus 1. Right, so somehow, one of the great discoveries of 19th century mathematics was to discover that the patterns in these numbers, when you fix this equation, when you fix the number 5, ask whether it has square root mod primes, as you vary the prime. People discovered this beautiful law called the quadratic reciprocity law, which answers the question, how do you tell whether the symmetry is 1 or minus 1? How do you tell, given a prime Q, whether this equation has 2 solutions or 0 solutions, mod Q? Right, so this was Gauss's famous quadratic reciprocity law, proved towards the end of the 18th century. It was conjectured by Euler and Legendre, and then Gauss, as a 19-year-old man, proved it. Right, so it's one of the great events in mathematical history. All right. So now, as I said, deep arithmetic arises by asking for the number of solutions of x squared minus 5 equal to 0 modulo primes q as you vary the prime q. right? You can, again, you can make a table. You can just make, and you're going to get a series of ones and minus ones. The question is, can you guess what the formula is? Can you, if you're just interested in computation, you just want a very quick way of telling what the number of solutions is of this equation mod q without actually doing too much computation, right? You want some formula. And it turns out that there is a formula, which is remarkable because one would typically think that this is like tossing a coin at every prime. It should be either 1 or minus 1, and there should be no rhyme or reason to whether it's one or the other. It should be pretty random. But it turns out there's tremendous sort of beauty. I mean, there's a kind of a beautiful pattern, and it goes by the name quadratic reciprocity. Again, any questions, or perhaps anything I've gone too fast over? Yeah. 5 is, again, not very important. I mean, you could do any number. I've just chosen 5. I mean, 1 would be not so good, but any number which is not a square would work. Yeah. Yeah. Yeah, so that is the province of quadratic reciprocity. Again, I'm just illustrating this for the purpose of the book. For example, I just focused on this particular equation. The quadratic reciprocity addresses all quadratic equations, all degree 2 equations, and patterns of how many solutions they have modulo primes q as you vary the prime q. So in fact, just to tie this up to my book, I recount this episode when I became as a high school student or something, very enthusiastic about number theory. I spent months reading about congruences and kind of all these things from, let's say, Hardy and Wright, which is a book on number theory. And I felt very proud of myself, that I've understood something. Okay, and then I went to Tata Institute. My sister had a friend whose father worked at Tata Institute. And when I entered his office, he asked me, can you tell me what the quadratic reciprocity law is? Now, I'm going to tell you that as I'll narrate now, the quadratic reciprocity law by itself is not that difficult, at least to state, right? But somehow I could not state it for the life of me. So which somehow the point is that in some ways, perhaps as you might be experiencing if you're looking at these ideas for the first time, sometimes when you learn ideas for the first time, congruences, there's that, in retrospect, it all seems rather easy, nice and simple and natural. When you first study it, you're kind of a little bit lost, so you don't fully understand everything. And so even something like stating a law, which is, as you'll see, has a beautiful statement, I floundered over, right? So that was one of the first setbacks of my mathematical career, after which there have been many. But that was the beginning. Anyway, so the quadratic reciprocity law says that this pattern of numbers you get by counting the number of solutions of x squared minus 5 equal to 0 mod q as you vary the prime q has a beautiful kind of, though it might seem random, one might expect randomness there. There's no randomness. It's totally kind of, it has a beautiful pattern. So basically, it has some periodicity mod 5. There's no obvious reason it should have this periodicity, but Legendre and Euler, great mathematicians, found these kind of laws just by, made a guess that this should be true, couldn't prove it even after decades of effort. And then Gauss, as a 19-year-old, came and proved it. Right? So somehow in mathematics, one is always has to be humble or modest, because somebody can just come along, a 19-year-old boy can come along and prove what defied you for decades. So, okay, so the quadratic reciprocity law says that these numbers you get, 1 minus the 0, you can ignore. These numbers, 1 minus 1, minus 1, 1, right, okay. So there's a pattern to these Galois symmetries at primes q, which is just nq minus 1. Basically, you're just counting the number of solutions of the equation x squared minus 5 equal to 0 mod q, right? So, okay, so skipping this thing, I mean, basically the law is that 5 is a square mod q, which is to say that the Galois symmetry is 1, local Galois symmetry is 1 at q. I wish I had a board too, okay. That nq is 1 precisely when q leaves a remainder of either 1 or 4 when you divide by 5. Right, so somehow the question of whether 5 is a square mod q purely depends upon what q is mod 5. Right, so this is this reciprocity law. So somehow you're kind of turning what is it called? You're flipping something. You want to know whether 5 is a square mod q, and that miraculously depends upon whether q is a square mod 5. Right, so somehow this is one of the astonishing kind of theorems in number theory. Of course, it's part of an elementary number theory course. The first course you'll do in elementary number theory, and let's say undergraduate level or something, will state this law and prove it. Gauss, over the course of his lifetime, found 9 or 10 proofs of it because he kept on struggling with it. He wanted to understand. Because even if you prove something in some ways, sometimes you feel you've not understood what you proved. Right? So he wanted to find a natural proof of it. And so even as great a mathematician as Gauss kind of wanted to come to terms with this rather uncanny law. And Somehow this, again, miraculously, this kind of Gauss's, this reciprocity law is related again to something totally different, which is the exponential function. Right? Somehow it's related to what people call cyclotomy. Cyclotomy phenomena of related to circle trigonometry in some ways. It depends upon writing. So somehow Gauss's proof of the quadratic reciprocity law. So first of all, okay, maybe I skipped a slide. Okay, I haven't. You can now kind of try to codify this pattern by defining this, what is called the Legendre symbol, in honor of this French mathematician Legendre, who struggled with this question, found these patterns but could not prove them. You define, so you say that this Legendre symbol, 5 upon q, right? It's equal to 1. Yeah, so quadratic is 5 is the square mod q precisely when q leaves a remainder of either 1 or 4 when divided by 5. Right? Perhaps you can now sympathize that why, as a 16-year-old, I did not grasp the quadratic reciprocity law fully when first I encountered it. But in some ways, because it's all about simple things going on. At least the proof is a different matter. Just to understand the statement in some ways is not rocket science, as they say. But still, it takes some time to absorb ideas, to reflect on them, to absorb them, and kind of know them fully. So I'm kind of presenting to you the confusion which I felt in high school. Okay. So basically all the takeaway from this is that you look at this equation, very simple equation, x squared minus 5 equal to 0. It has solutions, which we all know from high school, root 5 minus root 5. But when you start asking questions of this equation, how many solutions are there mod of prime? You get these numbers, which again, for a given prime number, you can just do brute force computation and figure out how many solutions are there, whether they're 0 or 2. But once you start writing them down, whether they're 0 or 2, strange, very beautiful patterns emerge. And then it took the greatness of mathematicians like Euler and Legendre to find these patterns, but they couldn't prove it. And then Gauss, as a 19-year-old, proved it. Right? So there's this beautiful story. And the quadratic reciprocity law has been one of the sort of canonical theorems in number theory and keeps influencing. Everyone wants to, people have tried to understand quadratic reciprocity law and keep it in more and more general context. And Serre's conjecture and the Langlands program, they're all kind of descendants of quadratic reciprocity. So again, this is something I try to bring out in the book, that mathematics, ideas never go bad, right? Once proved, something that remains proved. And even now, the mathematics of Gauss, 19th century mathematics, is highly non-trivial. One can get inspiration from it. It takes time to absorb those ideas. So the kind of long arc of mathematics, that's one of the beauties of the subject. All right, so somehow, as I said, this the proof of one proof of Gauss's quadratic reciprocity law is something to do with roots of unity of division points of the circle. I'm not going to go into too much of this. Okay, and so as I said, Gauss's quadratic reciprocity law started off again a series of developments which occurred in the 19th, 20th century, ongoing, where people try to understand what's going on. You're looking at equations, counting solutions, and observing patterns. How does one put this in a more general setting? One of the crowning theorems of number theory in the 20th century is what is called the Artin reciprocity law, which kind of is a massive generalization of Gauss's quadratic reciprocity. Okay, now the relevance of all this to our story is that Serre's conjecture is also a reciprocity law of some sort. Okay, so one of the crowning glories of number theory in the 20th century is the Artin reciprocity law. It was proved by Artin in the 1920s, and it generalizes the reciprocity law of Gauss to understanding more general Galois symmetries beyond the case of x squared minus 5 equal to 0. Right? I said that Gauss's law understands the symmetries of x squared minus 5 equal to 0. The symmetries you attach to it, modulo primes, as you vary the prime. You can do this for general quadratic equations, that is covered by Gauss's law. But if you try to do it for general polynomial equations, you come to mysteries. You still don't know. Even for a general fifth degree equation in some ways now, you still don't know an appropriate reciprocity law because you're going beyond what technically is called solvable Galois groups. Okay. All right, so this is a nice picture of Émile Artin, the person who proved in some ways the kind of defining generalization of Gauss's quadratic reciprocity. So this happened sometime in 1920s or 30s. Yeah. Yeah, Galois symmetries are somehow you're looking at the equation, looking at its equation solutions in complex numbers, and then looking at their symmetries. Local Galois symmetries are the same thing, you're doing the same thing, except you're looking at solutions modulo a prime. And so somehow the local means that they're local at that prime Q. Yeah. Okay, so important, so that was, so somehow Artin had understood in some ways certain kinds of Galois symmetries. More technically, there are Galois symmetries which are abelian, right? So somehow abelian Galois groups So Galois polynomials whose symmetries have some sort of commutativity property. Somehow Artin's law in principle understands what generalization of quadratic reciprocity to their context. Again, it was a hard one law because Gauss kind of proved his law at the end of 18th century. It took more than 100 years to discover the right setting, and to Hilbert kind of formulated some conjectures and so on, and then Artin proved it in 1920. Again, took more than 100 years to go from Gauss to Artin. Okay, so now what Serre and Wintenberger discovered is that the answer to Ramanujan's observations lay in certain Galois symmetries, which they tried to associate to the Ramanujan delta function. Right, so there's a story. So this is again, I'm cramming a lot of mathematics into. So I'm just going to want to give you a flavor of what's going on. So the unexpected patterns in the local symmetries arising from the equation x squared minus 5 equal to 0 is an instance of modularity. So Serre's conjecture, as I said, is a descendant of Gauss's law. And in the context of my memoir, this proving Serre's conjecture became my moonshot or holy grail after I started working in TIFR in 1995. So, okay, so what is Serre's conjecture? So Serre's conjecture seeks to understand Galois symmetries of polynomial equations defined over the rational numbers that are of GL2 type. This is so the conjecture is a converse to work Serre and Deligne had done, which attached Galois symmetries to Ramanujan symmetries. Anyway, so Serre's modularity conjecture basically conjures with these two different types of symmetries and kind of tries to relate them in the world of two-dimensional, the GL2 type symmetries. The abelian case had been understood by Artin. Right, so this is one, you're trying to go one step beyond. Instead of GL1, you're going to GL2. So each small step, right, takes tremendous effort. Even now, if you try to look at GL3, it's again terra incognita. So somehow so this is Jean-Pierre Serre, who is going to turn 100 next year. And he, okay, so guys, one of the features of these symmetries is that they're of totally different kinds. Galois symmetries are kind of discrete type of symmetries. They're often just finite. And while Ramanujan symmetries are very continuous, they're like analytic in nature. So Serre's conjecture, why it is astonishing, is that it's basically asserting Galois symmetries, which are discrete, are essentially the same as Ramanujan symmetries, which are kind of continuous in nature. It's relating algebra to analysis. So the surprise and power of the conjecture is that it intertwines these symmetries that a priori have completely different natures. Right? In mathematics, physics, dictionaries between two totally different looking things are very valuable. So Serre's conjecture is one such dictionary. Okay, so again, I'm not going to give you a technical definition of Serre's conjecture. It takes a while. So I'm just going to leave you with this thought that the Galois symmetries, which arise from symmetries of polynomial equations, there are Ramanujan symmetries, which arise as complex analytic functions. Serre and Wintenberger understood Ramanujan's conjectures by attaching Galois symmetries to Ramanujan symmetries. And Serre's conjecture tried to go in the converse direction. He wanted to go so known work went from a Ramanujan symmetry to a Galois symmetry. Serre's conjecture tried to go backwards from a Galois symmetry to a Ramanujan symmetry. So let me give a bit of the history of this conjecture. Serre had a very good friend at Harvard, John Tate, and the work of Serre and Tate was very influential in the 20th century to shape the course of number theory. So he made this conjecture to a letter he sent to Tate in 1973. So Serre has, of course, several volumes of collected works consisting of his papers. He also has several volumes where letters to Tate, letters to Grothendieck, right? So somehow he stimulated, I mean, his correspondence also is very interesting beyond the formal published papers. So he made these conjectures in a letter to his friend Tate in 1973. I don't know how much time do I have. I started maybe at 4, and what is the time now? Okay, no, right. I'll have to look at my. So he made these conjectures in 1973, and he refined these conjectures in 1987, stimulated by some remarkable observations someone had made about a connection between some very structural conjectures in number theory and Fermat's last theorem. Right? So Fermat's last theorem is this notorious problem from 350 years, which no one had been able to solve. And it always seemed a bit of a random problem, right? But somehow in the 1980s, Gerhard Frey, a German mathematician, observed that Fermat's last theorem would follow if you could somehow show this thing that Ramanujan symmetries and Galois symmetries are closely related. Right? So Serre was stimulated by this, but Frey's ideas were a little bit vague and could not really pin down what was going on. So Serre refined his conjectures to pin down what exactly Frey was trying to point out. Okay, so Tate's reply to Serre in 1970, so Serre sent a letter to Tate. At that time, there was no email. People corresponded by snail mail. So he sent a letter to Tate, and Tate, almost by return post, proved his conjecture in a particular case. So I'm using very beautiful but elementary arguments that one rely on Minkowski's lower bounds on discriminants of number fields, something one learns in a first course in algebraic number theory. He proved Serre's conjecture in the prime p equal to 2 case. In a very particular case, he proved his conjecture, and the proof is truly very number theoretic. It's making use of a very lucky fact that these two numbers, one is less than the other. Right? One is 2 to the 5 by 2, and the other one is pi e squared by 4. Right? And Tate observed in his letter that, okay, he's managed to kind of winkle out a proof of his friend Serre's conjecture for p equal to 2, because these conjectures are indexed by primes. So he could prove these conjectures for p equal to 2 in level 1, but he observed that his method has no chance of working for p beyond 5 for sure. And Serre, in fact, did generalize the argument to p equal to 3. And it turns out that this lucky fact, in some ways, is the starting point of our proof of Serre's conjecture. So these small cases proven by Tate and Serre turned out to be kind of crucial for this inductive argument we came up with for the proof of Serre's conjecture. Okay, so I'm now going to kind of not really let me kind of go to more to the qualitative description of all these things. So let me quote from my book. So Serre's conjecture is an organizing metaphor, right? Because I want to talk. As I said, my macabre-ish, foolish hope is that my book will be read by someone who's not a priori that interested in mathematics or doesn't have training in math. So I want to kind of give them a way of thinking about these two symmetries, because I certainly have not defined what these two symmetries are in my book, right? So some people need to be able to conjure with them and keep them apart in their mind and try to think that the fact that they're actually the same is a miracle, right? But on the other hand, then you have to distinguish these conjectures these symmetries in your mind. So I tried to make an analogy. So let me quote from my book. Serre's conjecture is like a beautiful metaphor which brings together two very different concepts, Galois symmetries and Ramanujan symmetries. To make an analogy with physics, one could think of the two symmetries as similar in a way to electricity and magnetism. In the 19th century, Maxwell proposed his equations that tied electricity and magnetism together, making them two aspects of the electromagnetic field. This gave rise to new physics that emphasized fields rather than mechanical forces and led to the uncovering of the electromagnetic spectrum and all its many applications. In an analogous way, Serre's conjecture unifies Galois and Ramanujan symmetries, two totally different kind of symmetries, and has powerful applications within mathematics. A proof of something else, which is called the elliptic symmetry conjecture, and Fermat's last theorem is a part of its potent force field, right? So somehow it's an organizing metaphor, and it's very, yeah. If you manage to prove it and its generalizations, you'll get lots of interesting consequences. So now my final act, I'm going to kind of skip a little bit, but the final act was when we actually proved this conjecture in the period 2004 to 2009. As I said, I'd started working on this conjecture in 1995 roughly, but then it took us 15 years roughly, or 10 years, 10 years to prove the conjecture. Okay, so now again, I'm going to skip all the, let me just leave you with the text, right, rather than, so again, now, one of the powerful things Serre did was tried to kind of quantify what kind of symmetry, try to attach numbers to a Galois symmetry. Ramanujan symmetries already came with numbers, the weight and the level, but the Galois symmetries were kind of named, had no attributes. So he attributed to them a weight and level. So Serre's conjecture, the weight and level of a symmetry are subtle properties of the symmetry, as little like the charge and spin of particles in physics. And somehow, okay, I'll skip a little. Serre said that these properties are preserved when you go from a Galois to a Ramanujan symmetry, that a weight k level n Galois symmetry should be the same as a weight k level n Ramanujan symmetry. And okay, so the last third of my book details the period when Jean-Pierre Wintenberger and I made a breakthrough in the proof of the conjecture. The initial breakthrough occurred when I visited Wintenberger in Strasbourg in fall of 2004, and a complete proof was published in 2009. Okay, and this is Jean-Pierre Wintenberger. He unfortunately passed away around 6 years ago. Yeah, but working with him has been one of the most thrilling episodes of my mathematical life. Now I'm going to skip all this and just leave you with one of the features of our proof, right, is that it uses an induction on prime numbers, P. Now actually there are very, very few arguments in number theory or in mathematics which uses induction on primes. Because primes in some ways, they're rather random things, they occur rapidly, 2, 3, 5. There's no rhyme or reason to how they occur, though statistically they have some properties. But kind of, so here's my thing. There's almost no successful argument in mathematics which uses an induction on primes. This is partly because prime numbers are sporadic, much too individualistic and unruly, with maverick and eccentric personalities to be able to cooperate with each other and act in concert. It was the magic. So one of the techniques of our proof was certain lifting. It was the magic of whatever we were using. It was the magic of minimal lifts and compatible systems that made prime numbers toe the line enough to make possible, in principle, an inductive argument on primes in a strategy to prove Serre's conjecture. Because what we observed in Strasbourg is, because of some things we did, that actually you could try and attempt to prove Serre's conjecture by induction on the primes P using the results Tate and Serre, or essentially Tate had proved for Serre's conjecture in the case of prime P equal to 2. So you could try to leverage that as a starting point and come up with some kind of rather fancy or elaborate inductive argument to prove Serre's conjecture in generality. Right? So somehow that was it was a thrilling discovery, totally unanticipated when we visited Strasbourg. And so now, okay, I'm just going to stick to the prose now and cut all the symbols. I gave a talk on the progress towards the proof of Serre's conjecture, roughly in perhaps 2005, at the Institute of Advanced Study in Princeton, focusing my proof on my proof of the level 1 case. I managed to prove the form of the conjecture Serre made in 1975 before he generalized it. I walked back for tea after the seminar with the prominent Princeton number theorist Peter Sarnak. He was excited by the talk and told me that proofs in mathematics that use induction and primes were exceedingly rare. Actually, what happened was that he told me that there is no proof which uses induction on primes, but I'm just kind of retrospectively saying that because this makes a better story. Anyway, so he was, and the one case we could think of, right, which used induction, was actually very coincidentally Gauss's first proof of quadratic reciprocity also used induction on primes. And it was kind of interesting because Serre's conjecture was in the lineage of quadratic reciprocity, and thus it was a nice coincidence, and basically it is, I think, nothing more than a coincidence, that Gauss's first proof of it and our proof both relied on induction on primes. Right? So this was kind of an interesting thing that, now let me end with saying that one of the things which happened, right, every kind of quest, there has to be some hazard and some sort of thing where you really have to fight the odds. So something happened towards the end of our proof when we thought we had proved it and then someone pointed out a mistake. So this had something to do with the prime 2. So we faltered in the final step of the proof. We had submitted our paper, a 100-page paper, to a journal, and the referee, through the secretary of the journal, we were conveyed this remark of the referee that certain lemma was wrong. And then it was a panic. I was just about to go and get a prize for the work, and but we kind of managed to patch the proof. So let me end. I think this is the last slide. Okay, finishing the marathon. This marathon to the proof of Serre's conjecture. The proof had we had problems with the prime 2. The last chapter of the book is called the oddest prime of them all. The joke being that 2 is the only even prime. The proof had survived, albeit with more work, demanding an emergency injection of new and delicate ideas to deal with the 2-adic results. So in some ways, that mistake referee pointed out, it took us 6-7 months to kind of fight it out. But in the end, luckily it worked, and it actually became an interesting part of our paper. Faltering, this again kind of illustrates the culture of mathematics, that people really study each other's ideas very carefully. They try to verify what's going on, and somehow that's one of the joys of math. That's one of the selflessness which calls for looking at someone's argument, really checking it in great detail, forensic detail. So we were lucky to have such a referee. So our faltering in the final ascent in our attack on the proof of the conjecture added an element of drama to the climax. Rajni, my wife who's here, was a steadying presence to the travails of trying to fix our mistake, and Arushi, my daughter, provided welcome distraction, because it was a rather sort of anxious moments we had. So it was good to have a nice, stable family life. Our mistake at the end was like the cramps a runner might experience when near the end of a race. Weary legs make the last few meters seem like an eternity. So I'll end there. Thank you. Yeah.
Thanks very much.
Yeah. Let me take some questions. Yeah, sure.
Yeah. So thanks very much, Shekhar, for taking us through that marathon, at least giving us some glimpses of that marathon and the broad impressionistic picture of a very vast, deep body of work. So more questions?
Yeah. Yes. Yeah, but if you look at the equation x squared plus 1 equal to 0, then and look at its solution mod primes q, and you vary the prime q, then it turns out that this has 0 solutions if q leaves a remainder of 3 when divided by 4, and it has 2 solutions if it leaves a remainder of 1 divided by 4. So again, this is again a particular case of quadratic reciprocity. This case was known to Euler. But yeah, so you, yeah, again, so you can use the, yeah, one proof of quadratic reciprocity does use roots of unity. So in the case of x squared plus 1 equal to 0, you're going to use these 4 roots of unity. Right. And yeah, somehow in this case, it's a little bit simpler than the general case. 5 in some ways is almost as difficult as the general case. -1 is a little bit, has more particular features, which make it easy.
Hi. Yeah. Hi. Just to get on this poetic touch with you using an induction of primes to prove this, as well as Gauss using an induction of primes to prove the quadratic reciprocity. As you mentioned that Gauss had also found a lot of other proofs for quadratic reciprocity, and many people have revisited that idea and proved them in probably 100 different ways now. Has the Serre conjecture been proven, or have you looked at other proofs of Serre conjecture, which do not rely on the induction?
Yeah, so at the time so initially when we met, Jean-Pierre and me, we had a strategy to prove Serre's conjecture. Now we were going to run into immense technical difficulties because we were going to use this method Wiles had developed, and when you tried to apply it, you were led to try and find generalizations of Wiles' method, which seemed technically very daunting. So our first breakthrough was to find a strategy. Then the next 5 years was to kind of implement that strategy and find ways so that we could get around all those technical problems. So now, in some ways, one of my colleagues has said, this kind of subject, the Wiles method, which is called modularity lifting, anyway, something, it's now become a science. Right? It has been generalized, it has been understood, but the proof of Serre's conjecture is still more like art, because somehow it's very tricky. You have to kind of find tricks. So the science so the proof has been simplified because Wiles' methods have been generalized. Still the strategy is the same as us. Perhaps induction is not totally necessary. There's some kind of induction, but it is a different kind of induction. Yeah. But some inductive feature is present in the proof. Yeah.
Just following up briefly on that, do you think it would be possible to have a kind of a structural proof at some point, in some way embedding it in some bigger structure which might make it almost tautologous in some way? Do you think that these symmetries...
Yeah, one hopes. I mean, there's of course what is called the categorical Langlands program, which people hope might eventually kind of give some maybe ideas of physics. And so there's hope that something dramatic might happen, but it still seems like a distant dream at this point. Yeah. Mm-hmm. So just now, for example, I mean, our proof, for example, uses happy coincidences, right? So even simplifications of the proof, they use this starting point. You need a starting point, and the starting point is provided by Tate, and it uses this inequality of the two numbers. Yeah. And so that's an accident. And if you try it, Serre's conjecture is, as I said, we proved his full conjecture, but that conjecture can be generalized. And when you try to generalize the conjecture, our proof breaks down. So the conjecture generalizes, but the proof doesn't generalize. The ideas might generalize, but there's no starting point. So we are left with...
You mean GL3 or something?
Yeah, GL3, or if you, instead of working with the rational numbers, you work with number fields. Okay. Consider modular forms and Galois representations over Q square root of 5, for example. Mm-hmm. I mean, this case might be doable, but in some ways the conjecture takes a lot of work, and actually no one has managed to prove any case of this kind of conjecture beyond what we did. Yeah. Though there's active work, though.
I mean, that numerical coincidence that you showed, I think you didn't have that in the book, I think, right?
Maybe in the footnotes I might have it, probably not.
Okay, but in any case, so is there you said that when you do the induction, do you have like a chain of such inequalities for different primes? You just need that one. It's not like there's something analogous.
Actually, so initially when I was trying to get more and more cases of Serre's conjecture, we were trying to draw upon other such numerical coincidences. But as I make this analogy, because this book tries to make analogies, so I'm saying that it's like somebody in the Gulf state discovering oil, and then your economy is living off oil, right? And then somehow you're going to exhaust that natural resource. You have to find a way of sustaining an economy which is not drawing upon a natural resource which is going to exhaust itself. So the way we found a method to the proof is we managed to wean ourselves off making use of these coincidences beyond the one Tate had used. That one Tate has used is locked, is really there, but no other further coincidences are needed, further accidents are needed. Yeah. So one of the themes of my book, again, is that you need luck. You need luck in mathematics. I mean, you need luck in anything in life, right, to be successful. But here we were lucky that, first of all, we found these ideas, and we were also lucky that Tate had proved this initial case, which was itself based on luck. So there's a lot of luck in the proof. Yeah. Yes.
So I want to ask how much of your proof, you said you spent, 10, 15 years on it. How much of it did you spend developing new theory, as in new rich theory, not just theorems, a complete theory like I mean, Andrew Wiles did that with the Fermat's last theorem, right? He proved so many things which, I mean, he discovered so many things along the way that it became like its own theory and everything. So how much of that went into your proof?
So our proof, in some ways, the main idea was just a strategy. So in some ways, I think of myself as a problem solver. I'm not a theory builder. So we kind of solved a problem. But of course, if you solve a problem, it can become the basis of a theory. So the methods we've discovered are used and they form a body of work. But in some ways, we had a strategy, and then we tried to draw upon Wiles's methods. But on the other hand, Wiles's methods, we ran into problems because it's kind of rather technical. So we had to find a way to use Wiles's methods, which were efficient and which would allow us to implement our strategy. In some ways, the main originality of our work was to find a strategy and then get to. So it was more of a problem-solving kind of thing rather than theory building. Yeah.
There was some question there somewhere. Yeah, sure.
Yes. Yeah.
The question I have is slightly related to the previous question. So you said Serre's conjecture implies Fermat's last theorem. So does that mean that if Wiles hadn't come up with his proof, you would be the person who had proved Fermat's last theorem?
No, because I mean, our proof draws upon Wiles's results.
Yeah, so that's why I said it related to the previous question.
Yeah. But actually, as I say somewhere, I mean, when Wiles announced his methods, his proof, he said his methods were orthogonal to Serre's conjecture. Somehow he was avoiding trying to prove Serre's conjecture. Because somehow it did, so that's why it took so many years after Wiles did his work to prove Serre's conjecture, though people were trying. Because in some ways, there seems to be almost a logical conundrum, because for Wiles, the logic of Wiles' proof is assume Serre's conjecture, and then you deduce something else. But he assumed Serre's conjecture in a very particular case, in which case it happened to be known. But that was, again, it was like the state kind. Some very particular case of Serre's conjecture was known, and he could leverage that by his beautiful arguments, by his really magnificent mathematics. He could leverage that known case to prove what is called the modularity conjecture for elliptic curves, and as a consequence get Fermat's last theorem. But our proof, we prove Serre's conjecture. It also gives a simplified proof of Fermat's last theorem. Wiles had to use all kinds of, ours is a cleaner proof, but it relies on Wiles' ideas. So one can't say that we could have proved it. Yeah.
So any motivation for Jean-Pierre Serre's conjecture? How did he relate the two seemingly unrelated objects? One discrete, one continuous.
Yeah. Actually, I recount that in the book. For example, when I was working at TIFR, maybe around 97 or something, 1997, I made a very small observation that his conjecture implied something else, which is called Artin's conjecture, and the same Emile Artin, this French, German mathematician. It implies Artin's conjecture. And so, in fact, when I sent that argument to Serre by email, I think he was at Harvard or something at that point, he replied to me, I wrote to him sometime Bombay afternoon, he replied to me saying that he doesn't believe the proof, it's nonsense. But then I tried to argue with him and persuaded him in the end that it worked. It was a very simple observation. It's not that difficult, but Serre kind of psychologically was not prepared to think that his conjecture implied Artin, because his motivation for making his conjecture was the Artin conjecture. So there was some kind of conjecture over complex numbers, which, if you try to think about the analog of that conjecture over complex numbers, mod P, you're led to Serre's conjecture. So there was some model. So it's hard to think. It's hard to say how he came up with this conjecture. In the retrospect, it seems natural. He knew how to go from a modular form to a Galois representation, or in this language, from a Ramanujan symmetry to a Galois symmetry. And then the natural speculation one can make is there can be no other way. So all Galois symmetries should arise from Ramanujan symmetries, and somehow that was his conjecture. But it arose from the work he did with Serre and with Swinnett and Dyer. He had been thinking about these things, and he had a model in Artin's conjecture, and yeah, so that's. Yeah.
So
it is just a very formal analogy.
Yeah. No, but is there a corresponding in your proof about the electromagnetism together? Is there a bigger group of symmetries from which these two?
Yeah, not that,
really,
right?
not like that. Okay.
We just have to find a way of passing from one symmetry to another, which they're totally different. So somehow it's a very indirect argument. It's hard to kind of, but it has this thing that it uses induction on primes, which is, or it uses induction on several, it uses induction on primes, it uses induction on the level n, the weight k, whatever parameters, numerical parameters are involved, we induct on them. Yeah, Jaykumar had a question. Yeah. No.
No. So did Serre also have a model for how the proof might go?
No, in fact, Serre, I think Serre once told me that he has never worked on his own conjectures because he thinks he has done his job and it's the job of the other people to prove it.
So in the spirit of getting an insight into how mathematicians' minds work, how does one go, how does one go about formulating a conjecture? There must, is there something you can say about that?
So, in the case of Serre, I mean, you're working with some mathematics and, I mean, it's basically, it's like in fact, I've had my book, I would read from it. I try to make this thing that a conjecture reflects the sunny yet cautious optimism of mathematicians who work them. If the conjecture were true, it would be great. It would bring coherence to a subject. So you're just thinking that if something would be true, then there would be explanations of various things you're observing. Right? So somehow, I mean, Serre had attached a Galois symmetry to modular forms, Galois representations to modular forms, Serre and Delin and various people. And the natural question was, is the converse true? Is the only way to make a Galois representation in this particular kind one coming from a modular form? So it was just that's why in some ways it's a reciprocity kind of conjecture. You know one direction, you want to go the other direction. So yeah, so it was just a natural guess. Serre had certainly, it was fantasy when he made the conjecture. There was no way to even think of proving it. There was no methods. So there was no way even you could start thinking about the conjecture. So even when I was a grad student, I mean, I knew the conjecture, but one couldn't even begin to kind of think of fooling around with because there was nothing you could do. But Wiles' methods kind of transformed the situation where somehow there was some new idea in the air and there was hope in show it hope that you could kind of try and do something.
So the last question, because we have to clear the auditorium for the performance. Yeah, Gautam.
Yeah. So again about conjectures. One keeps hearing about Ramanujan's conjectures. Something that has been proved after 6 decades, something yet to be proved, and so on. My question is, has there been any Ramanujan conjecture which has been proved to be wrong?
So actually, I'm certainly no expert on Ramanujan. The only paper of Ramanujan I know is the 1916 paper. Right? So I wouldn't know. In general, I think his intuition was remarkably strong. Whatever he guessed but I wouldn't know if there is. Yeah, I don't know.
Yeah, I believe there are statements in his notebooks which are not exactly correct, but they are often very creatively wrong. I think so. That's what at least.
Maybe I can end with like I talked to Serre about Ramanujan because Serre and Ramanujan are opposite types of mathematics. Serre is French, very precise, kind of doesn't even in a lecture he hates somebody being ambiguous, and so while Ramanujan was all about intuition, right? Somehow he wouldn't be able to explain how his ideas. But someone like Serre has tremendous regard for Ramanujan because, for example, for this 1916 paper, maybe he knows papers beyond that of Ramanujan, because in some ways even he says about André Way, for example, that André Way saw the future. So similarly, for Ramanujan, in some ways there was something prophetic about Ramanujan's work, that he could see things which the present state of mathematics would not be able to prove, but he could see things. And seeing things is very important, right? And so even in some ways, I would have thought Serre would not appreciate Ramanujan. They're very different types of mathematicians. Also, for example, Serre made this remark because Ramanujan somewhere, or at least he's alleged to have said, I don't know whether he actually said this, that that the goddess Namagiri or the god Namakala, they placed formulas on the tip of his tongue. Right, so Serre was telling me, he tried to make sense of this from his own point of view, because probably he doesn't have the same religious viewpoint as Ramanujan. But the way Serre understands this remark is that Ramanujan, and Serre knows from personal experience, that one can get ideas when one is half awake. Right? So Serre thinks that Ramanujan used to get his ideas when he was in a state of half wakefulness, and then So this is kind of and one more remark of Serre is that, in relation to my lecture, is that I asked Serre whether Ramanujan knew what the definition of a modular form was. Right? So Serre said he may not have known, and it's not relevant because he knew enough to do what he did. So, for example, for some people who know a little bit about this stuff, when Ramanujan looked at these Euler factors for the Ramanujan delta function, he factored those polynomials he got as a product of two linear factors. So he identified there was some degree 2-ness to whatever he was doing. So in some ways, Serre thinks that Ramanujan intuitively knew that there was some GL2 stuff going on. So somehow, again, this is just one great mathematician, Serre, of a completely different temperament from Ramanujan, being kind of, in kind of awe or appreciating a totally different type of mathematics and taking inspiration from it.
Great. Thanks very much again, Shekhar, for engaging with us and carrying us through this.